to 656, as that speed is to the speed of light. It's just a proportion, right? The shift is to the total wavelength as the velocity is to the total speed it could go, right? So 35 divided by 656 times 3e8. Wow, that's a lot of speed. Let's see. Doot. Do you guys get that the velocity is 1.6 times 10 to the 7th meters per second? Yeah? How many kilometers per second would that be?
That would be
1.6 times 10 to the 4th? Recession velocities typically are in kilometers per second just because they're so fast. Yeah? That's pretty fast, yeah. Okay, so what this means, here's what it means, right? This guy Vestos Slipher looks at all these galaxies. They're all redshifted. Redshift means that they're moving away from us, and they're moving away from us really fast, right? And then, you know, now we've got a 100-inch telescope on Mount Wilson. Mount Wilson's right above Los Angeles, yes? Yeah? There's snow up there. Like, you can get down there. You can get there in like the spring. You can go up to Mount Wilson. There's snow. You're like sweltering in heat in Los Angeles. There's snow up there. Yeah, you can have a snowball fight. This is a very fun place to go, right? And the 100-inch telescope allows him to not only see that these spiral nebulas are actually made of stars, that the Andromeda galaxy is another galaxy just like our own, but he can actually pick out individual stars on there. And there's certain stars called Cepheid variable stars, right? That are distance indicators. We know how bright they are because of how they vary in brightness, right? And he can pick those things out, and he measures Cepheid variable stars, and he calculates the distance to those stars, and he calculates their recession rates, and he does this for many galaxies. There's a relationship, and I don't know if you can see the relationship here. Is that a relationship? Yeah, the farther away something is, the faster it's moving away. Yes? Yeah, so this is this notion, right? This is this thing, right? The farther something is away from us, the faster it's moving away from us, yes? Yes, there we go, right? So this is the expansion of the universe, and this is Hubble's law, and it is very, very complex, okay? It's a very complex law. I don't expect you to understand the intricacies of multiplication at this age, but let's just try, okay? But basically what it says is that the distance here, and this is so subtle that you have to actually deal with megaparsecs. These are millions of parsecs, okay? But basically your recession velocity is some constant called Hubble's constant, because, you know, there he is, right? Times that distance. This is the distance to the galaxy in megaparsecs. To the galaxy in megaparsecs, right? Okay, this is some constant, and we have a really good idea what it is. It could be 50 or 70. We think, by the way, it's about 71, plus or minus about 1 or something like that, right? Okay, but basically, if you know, in college they say that it's 80, humor them, right? They just haven't read. There's recent research. They think it's they're pretty sure it's like 7.1 plus or minus 1.3 or something like that. Okay. But this widely ranged. We went from 50 to 80 to 100 or something like that for this, right? And then this guy, so this is a constant. Notice that it's 71, I think, kilometers per second of recession velocity per megaparsec of distance. So when you get a velocity, it's going to be in what? It's going to be kilometers per second, right? So that's recession velocity in kilometers per second. So if it's not in kilometers per second, put it in kilometers per second, right? The distance you get, if it's not in megaparsecs, put it in megaparsecs, and then you're good to go, right? I don't think I play that game with you, but I could, yeah? So put that in your notes. What is the distance to a galaxy that has a 480 nanometer line that comes in? Oh my God, is this a two-step problem? Yeah, it crazy is. So what's the first thing we do? Is she asleep? That's funny. Okay, so anyway, the first thing you want to do is definitely, recombobulate the synchrotron, right? Because you basically want to keep the same sort of noise level going. Because if the noise level ever drops, then, then basically blah, blah, blah. And then the thing that's going to happen is going to be really quite loud because of the expansion of the universe. Okay, so really what's going on here what's going on there is that right after the Big Bang oh okay. I did something else. I thought this was really funny. Was Braden Schoonmaker fell asleep, right? And so I snuck up to him with a Nerf gun, and when I was really close to him, I just went, ah! And when his eyes opened, I sort of pummeled him in the face with these little Nerf balls. Some people take offense at that, though. It's like, you're singling me out. I don't know. This was okay. So this is going to be a two-step problem. Okay, the first thing we're going to do is we're going to use the redshift to figure out the recession velocity. So we're going to use this formula first, right? And then we're going to use our new formula to figure out our distance too, right? Okay. So the first thing I'm going to do is I'm going to set up that guy. What's our shift in wavelength? 17. Yeah. So our shift in wavelength, and then this is what is this? This is V over C, right? So when I do this guy, this is going to be 17 divided by 480. Now, how do you know which F to put down there? There are two F's, correct? Notice that I say that it is a 480 nanometer line, so that's what you do. What it is what you put in there, right? Okay? So 17 over that equals whatever that velocity is over 3 times 10 to the 8th meters per second. Yeah? And now we're set. We can figure out that velocity. Okay, so 17 divided by 480 times 3e8. Hopefully, were you having like a dream? Were you having a dream like that involved explosives or something? No. Okay. So anyway, this velocity is 1.06 times 10 to the 7th. Yes? And this is kilometers. Whoops, this is... Yeah? So I get this number, yes? Do we get this number? Yeah. And then I turned it into kilometers per second. Why did I turn it into kilometers per second? Because I needed to use this formula. Very important point. Hello? Very important. In fact, the IB kids, by the way, just took this test, like the really fancy IB2 kids, right? They just took this test on it, and they forgot to do this, right? And I gave them a really hard time about it, so here it is, right? So you get this velocity. If it's in meters per second, turn it into kilometers per second, because this is kilometers per second. The recession velocity has to be kilometers per second, or it doesn't work, right? So now we're set. Now we can use our new formula, which is V is HD, high def, right? Okay. So 1.06 times 10 to the 4th kilometers per second is, what do they say to use, 71? So how do we solve for D? Is it just dividing by? Yeah. Is it just divided by? Okay, so I'm going to divide this answer by 1,000. And now I've got kilometers per second. Now I'm going to divide it by 71. And I get a lot of megaparsecs, 149.6 megaparsecs. Megaparsecs. I would have thought the mega would have woken you up. Mega! I don't take it personally anymore when kids fall asleep. I just, but what I do like is when you do sort of like some terror tactics like that where you like run up and scream and right, it doesn't help them stay awake like the next day.